I'm Ed Carls. I'm a grad student at the University of Illinois. I'm working on parallel I/O performance. So I'll talk about some of what I've discovered about I/O performance on Blue Waters and what you can do to help improve your code. First of all, we'll talk about some of the main factors. Then we'll talk about getting to know the I/O in your code, some profiling tools, what striping can do for you, data layout issues with your program, and then finally a little bit about collective I/O. So the most important thing in your I/O performance is the length of each basic operation, how many bytes you process in each read or write operation. The disks can be pretty high throughput, around 500 megs a second for a single process, but it's pretty high latency. So you really want to have lots of large reads or writes, not lots of little ones. Sorry, a small number of large reads and writes rather than many small ones. And also, the locality matters a lot. There might be a little prefetching involved. So if you jump around the file a lot and do a lot of seeks all over, that also really kills the performance. So first of all, just to show what performance is possible with a single process. So the red is read time and the black is throughput. Read throughput and write throughput. So you should be able to get about 500 megs a second read throughput and a little over 600 megs per second write throughput. Notice the operation sizes starting at the left end, 32 kilobytes at a time, up to 16 megs at a time. So at 32, it's pretty close, but basically anytime you're over 64K or 128K, you should be getting the full performance. But here's what happens when you go smaller than that. It plummets. Notice on the left side, that's a logarithmic scale. So if you're writing 4 bytes at a time, you see absolutely abysmal performance. This, I think, is the most important chart I want you to see. The size of your I/O operations is critical. You really need to use nice, large reads and writes. Next, I tried, so with this data, it was just reading and writing one big contiguous file, or contiguous reads and writes, just a whole stream of them, not moving around. Here, I took a big file and just kind of jumped around randomly. And again, that's logarithmic scale on the left. You can see with very small operations, it's getting 0.0001 megabytes a second, so hundreds of bytes per second. So try to avoid seeking a lot as well. Now, I've been working with a couple teams trying to get to know their programs and get to know their I/O, and that can be challenging because your I/O is going to be 6 API levels deep inside your program. But it's important to know what the shape of your data is, what data each process is acting on. So you'll have a large data file, and each process is probably only interested in a small part of that. And is that small part one contiguous part of the file or some subarray of an n-dimensional grid? Also, text or binary. With the profiling tools, it doesn't even catch I/O that's done using printf and scanf because it's just assumed that the performance will be so terrible. Try not to use printf and scanf. If you are using nice big reads and if you're printfing a megabyte at a time, it might not be so bad, but they generally perform pretty poorly. Now we have a profiling tool called darshana. It's automatically on. You can disable it if you are worried about the performance hit, but as far as I know, it's pretty minimal, although I should get some data on that. And yeah, so you can disable it with a module on load before building your program. Now all the logs are in a publicly accessible directory, so you can see the names of some of your files. So if you're dealing with classified data or whatever, you may want to disable that. But if you look in that directory, you'll see a different directory for each month of data, and you might have to go through. There's a couple indexes and tar.gz files, but once you look up the index, you'll see your username and the job IDs, so you can scan through that and find the darshana data from your runs. Now, just a caveat, darshana only produces output if your program completes successfully with a call to MPI finalize. So if it crashes halfway through, you won't have any darshan data. Here's just a sampling of what the darshan data looks like. It's mostly summaries, like how big are the I/O operations? Are you accessing, do you have many processes accessing a shared file, or do you have one file per process? Just basic summaries that, it gives you a general sense for what your program is doing. And this is a sample of the PDF output it can produce. Here's the darshan commands. The Perl script up there at the top, you give it one of your darshan files, and it generates a PDF report with all those summaries. And you can get per file summaries, or if you just want all the raw data that darshan collected, you can extract that with the darshan parser command. Now, one thing I just noticed as I was preparing these and testing things, we recently upgraded to darshan 3. And you can tell which files were created with darshan 3 versus darshan 2. Darshan 2 automatically gzips everything and has the gzip extension. Darshan 3 doesn't. It might be gzipping internally, but I think it just doesn't. So if you try to feed one of the gzipped darshan 2 files to darshan 3, it complains and says, I can't even read the version number on this. So if you have look at your log file. If it doesn't have the gzip, it's probably darshan 3 and shouldn't need any changes. Just those commands here will just work. If you have an older file, older as in more than 2 months ago, you might need to switch darshan version to 2.3, and then you'll also have to disable the new version of GNU plot because it relies on a slightly older version of GNU plot. So Blue Waters uses the Lustre file system, and it's this whole complicated setup of a hierarchy of RAID disk drives and cabinets of disks. But essentially what it gives you is 360 OSTs. That's a Lustre terminology for a file server. It's essentially 360 independent file servers. Now, you can tell with when you create a file, you can say, take the data for this file and distribute it across some number of file servers. So for example, here at the graphic there, I tried to demonstrate a file split across 4 servers. You tell it how many servers you want and how large the stripes are, how large those chunks are. And it will distribute the data for that file across the file servers in a round-robin fashion. So this lets you get parallel throughput for a single file. There's a command line tool to set this. You can also do it with MPI IO. I'll show that in a sec. But if you just want to see the striping parameters of your file, you can just say LFS get stripe on a file or directory. And so there we see the stripe count 4 and stripe size of 1 megabyte. Let's see. Now, if you set the striping parameters for a directory, I don't think they affect anything about the actual directory storage. That's got its own metadata scheme with Lustre. But what it does is any file you create in that directory, if you don't otherwise set its striping parameters, it'll inherit them from the directory. So if you want all the files in a directory have some such striping parameters, just set it on the directory and it'll inherit it. So set stripe, here we have size and count. There's a bunch of other flags, but haven't found much use with them. Set the size of each of the stripes, and you can use M suffixes for megabytes. I think it's best to do it in megabyte chunks. I think that's its fundamental unit size as opposed to traditional hard disks, which are maybe 4 kilobytes or 512 bytes. You want to think in megabytes with Lustre. So with directories, it'll set the inheritance, and with files, it's important to know you can only set it at the time you create the file. Once it already exists, it can't change the striping. If you do LFS set stripe on a file that doesn't exist, it will create an empty file with your desired parameters. Now, if you have a file that you want to change the striping for, what you can do is create an empty file with the parameters you want, and then just use the CP command. And it will transfer the contents into the new file with the new file's striping parameters. If you're using MPI IO, you can set these, the stripe size and stripe count with a couple info hints to MPI file open, the striping factor and striping unit. Now in Blue Waters, The home and projects file systems have 32 file servers on them, 32 OSTs, and Scratch has 360, or they might have more, but that's the most number of stripes you can have for files on those file systems. But when I was playing with this week, I noticed that I can't actually set a file directly on Scratch to have more than 36 stripes. But I can create a directory that says to inherit 360 stripes, and then any files I create work. Yeah?
So this was on Blue Wire this week?
Yeah. Good. Someone's looking to do it. Thank you. So I'm not sure what the deal is with that.
We changed the wrapper for LFSF stripe, but apparently nobody tested that. So we need to fix that.
Okay. Good. Yeah, no problem. Yeah, it complains that it says, even though I'm on Scratch, it says on home and projects, you can't have more than 36. So, but you can work around it. So here's the I/O performance I was able to get. I think this is write throughput with a single file with different levels of striping from 1 stripe to 128 stripes. I got a maximum, so with a single stripe, I got about 500 megabytes per second, same as before. And with 128 stripes, I got 43 gigabytes a second. Now this is older data. I think I did this last fall before we changed the file system. Which now supports more stripes. I think at the time it was limited to 160 stripes. So I want to rerun this. I assume it'll only be better, but yeah, this may not be accurate anymore, but gives you a sense that adding stripes can improve the performance to at least 40 gigs a second. Now, yeah. Yeah, I think I was writing from, I forget exactly how many nodes. I think I matched the number of nodes to the stripe count. So the biggest one was 128 nodes, and writing from, I think, 8 processes on each. So here's some stats from the milk code I worked on. I tried playing with the stripe size. We had just been talking about the stripe count, how many servers we distributed across. But now I tried playing with the size of each of those stripes, everything from 4 megabyte stripes up to 64 megabyte stripes. And we got a very nice performance improvement. So notice that's the time on the left, not the throughput. So the lower numbers are better. And the 64 meg stripes were over 7 times faster than the 4 megabyte stripes, which seems to say that large stripes are better. But then I reran it with a simple code that just does straight I/O, and it just kind of jittered at about the same value for different stripe sizes. So first of all, the lesson here with the I/O, it's very jittery. It's hard to get reliable numbers because you're sharing the computer with 1,000 other processes, so you never know if someone else is going to come in and start beating up on the disks while you're testing. Also, the stripe length, it probably just depends on the application. I don't have any good guidance on how to choose stripe length except to say that I'm pretty sure you want it to be at least a megabyte. Let's see. Now, that was all talking about a single file, striping one file across many file servers. You can actually get better performance if you create many files. It's just more of a hassle because you have a zillion files floating around. And this can cause issues because every metadata operation, every LS, when it's just doing a directory scan, can get pretty slow when you have zillions and zillions of files. With I think it's the Gadget team yesterday were showing how with their big data or big file system, they were getting great throughput, like around 500 gigabytes a second, and they had a whole hierarchy of zillions of files. So I think, yeah, I think that was the key to their performance. They use zillions of files, but to minimize the metadata so you don't have gigantic directories, they created a whole hierarchy of them. So each directory itself isn't all that big. But it gets to be a hassle, and this is something we want to try and figure out a better solution on this so you don't need a zillion files. But when you do have a zillion files, you probably just want each one to be on a single file server, so just set their stripe count to be 1. And as you create these files, each one will be randomly assigned one of the 360 file servers. Well, I suppose it probably isn't random. I think it tries to balance the load on each of the servers, but it's essentially random. So here I tried testing the throughput for varying number of processes and number of nodes. So starting with one node running everywhere from 1 to 32 processes on it, up to 256 nodes running 256 to about 10,000 processes with one file per process. So with this, I was getting just north of 100 gigabytes per second, keeping in mind that there's 10,000 files in the directory. So you can get better performance with a single file per node. It's just a little bit more of a hassle to manage your data. This is zoomed in on the upper part of that graph. So with between 1,000 and 8,000 files, here we see the throughput getting, they're about 153 gigs per second. So overall, about 3 times more throughput than we did with a single file, with, I think, a similar number of nodes. And now the number of nodes is significant with the I/O. There's only so much throughput from each node to the file servers. So as you add more nodes, it opens up more throughput. That's one of the ways Gadget was able to get such great throughput. They were using the entire machine. They had every node. So the data layout can cause issues. Remember how I said you want nice long reads. A common data format is to have an n-dimensional array. And if you think about how that exists on disk, it's just like in memory with a, forget the terminology, with a Fortran versus C arrays, whether it's row major or column major. If you start going down the columns, it's going to be doing a disk seek each time you change rows. So if you have multiple files, say we've got a simple diagram of here's our data file, and we have 16 processes. Each of them wants to access one tile of data. To access those, I'm afraid to touch the laser, it's going to do lots of little reads, like one little read of that, then the next row, little read. So lots of little reads, and this is a performance killer. So this is where we want to do collective I/O, where each the processes all kind of say what part of the file they want, and then some subset of processes accesses the disk and does big, long, contiguous reads. So here we see process 0 reads the top quarter of the file and then shares its data with process 1. Process 1 reads the second quarter of the file and shares part of its data with process 0, so it can get part of its tile. So all the processes say what part of the data they want. A subset of those do nice big long reads or writes to access the data efficiently, and then they shuffle the data between themselves. And something to keep in mind is that the disk throughput is far slower than the point-to-point interconnect on Blue Waters. So you don't want to use the disk much, you want to use point-to-point MPI commands. So the good thing is collective I/O, it's built into MPI I/O. It's there, it's been there for a while, it works pretty well. The problem is you have to use MPI data types to describe these subarrays. You describe the size of the full array, and then you describe the subgrid that you want, and it gets to be a little pain in the butt. I tried to make it easier. I made a library called Mesh IO that lets you do collective reads and writes on these subarrays, and I think it makes it a lot easier. Rather than 30 lines of setting up MPI data types, you can just have one big call with a bunch of array definitions, just as simple arrays. It works with any level of data, not just 2-dimensional. It can have 5-dimensional or whatever, and it handles byte endian issues for you. You tell it, in case your data happens to be in big endian and your little endian, it won't detect that, but you can tell it, do the endian swaps for me. Yeah.
Are you going to talk about Mesh IO anymore here?
Briefly, yeah. Okay. Now, Parallel HDF5 and Parallel NetCDF, I'm pretty sure they both have this built in there as well. Be sure to use the Parallel HDF5. Straight HDF5, I think it does lots of little reads like this. You want to use the Parallel HDF5. It uses the collective I/O operations and should perform a lot better. And just briefly showing my interface for the Mesh IO, it's not a whole lot of code. It's basically a thin wrapper around the MPI IO routines, adding stuff like endian handling, and you can set the memory array order. If your disk is in Fortran order and you want to read it into C order, it can handle that switching for you. So you just define the size of data you're interested in, what the file itself looks like, and what your memory array looks like, just in case they don't align exactly. So you had a question?
If you're looking at just a single chunk of data, as far as like each row, is there any particular maximum that it has? Can it be up to like megabytes?
Is there a maximum to the size of a row it can handle? No, can be anything. Now the collective I/O routines, they define some buffer. They don't read in everything all in one. I think they have a buffer of around 4 megabytes. So it'll transfer 4 megabytes at a time and handle all of the data shuffling between processes. And this is on GitHub. If you have n-dimensional data, yeah, give it a shot, see if it works well. And it's a collective operation. It uses MPI files. So when you open an MPI file, you give it a communicator, and you have to make sure anytime you call this, you need to be, every process in that same communicator needs to be accessing this for the collective operation to work. And so this is the mesh IO read, mesh IO write is exactly the same, except the data is constant, I think. Here's an example of a program that used mesh IO. They were doing they were accessing the n-dimensional array by doing, let's see, they had multiple versions of the code. One version did lots of little reads. That didn't perform well, so they switched it so that every process read the entire file, but only saved the part it was interested in. And that kind of killed the file server, so they put in a bunch of barriers to serialize all that. So among the 1,200 processes, each of the 1,200 processes would read the entire file, saving just the part they wanted. And it took about 90 minutes to read the whole file, but so far it was the fastest way they found to access it. So I switched it to use, so here, yeah, so this is the increasing number of processors, but with a constant data file size, just 1 gigabyte. Shouldn't take too long. But the time to process it grew in proportion to the number of processes. So here it took an hour and a half to read the thing. So once I switched it to MPI IO and my mesh IO, it's consistently under 1 second for the read portion of the thing. And I got to delete a whole bunch of code, like, you know, delete about this much code and replace it with one little call to mesh IO. So that was a nice win. Now, one thing to consider if you're doing bioinformatics data and anything else that's very compressible, consider storing your data compressed. If you're going to be reading it many times, take all that file full of AGTs and Cs and just store it compressed with gzip, bzip2, or whatever. And that kind of gives you an instant multiplication in your throughput. I had a sample data file. It was 40 gigs in it originally, and I think I used the Facebook's Z standard compression algorithm, got it down to 275 megabytes, so about 150x shrink. And with my laptop, I can do a serial scan of that file in 9.5 seconds. So this isn't necessarily improving your Blue Waters project, but it makes it so you can sometimes take your Blue Waters data and run it on your laptop. I can see a situation where it might take 2 hours to run on your laptop, 2 minutes on Blue Waters, but you get to save that 2 hours you would sit in the batch. So I've got two APIs I've been playing around with. zchunk, which takes a data file and compresses it in chunks and lets you extract data. You just give it a byte range. And then zlines, where it compresses chunks of lines of text. And you reference stuff by line number. Now, zchunk, I'm pretty sure that's similar to something built into HDF5. So I'm sure their code is more mature, but I just wanted to try it out and see what performance is possible with this. So these are experimental, but they're on GitHub if you want to play with them. So in summary, make sure all your I/O accesses are big, at least 64K. For best performance, use lots of files. With a single file, make sure you enable striping to enable parallelism with that. And you can use collective I/O to avoid doing lots of little accesses. Any questions? Yeah.
So when you say you use lots of
current recommendation for lots of little files, I think hundreds is a good number. More than that, it gets to be a bit of a drain on the metadata operations. But the fact is, as you create thousands, the performance still does improve. So for absolute best performance, yeah, I don't know what the upper limit is. I haven't done runs more than 256 nodes. I just know that as you get really large, you can overload the file servers and they just get clogged. So I would say it's safe to have hundreds of files, but not thousands. Yeah.
I'm using the Fortran direct access files to write records and each process to write separate records. Is that a really bad idea and I should think of switching to MPI IO?
Yeah, so using Fortran IO with a direct record access, it's probably not going to have very good performance unless the records are, 64K long or more. You're probably better off using MPI IO.
Yeah, pretty big actually.
Yeah, as long as they're big enough, then it should be fine. Yeah. Any other questions?